the last lecture, I mentioned that linear vector spaces are very important in understanding the structure and framework of quantum physics. So today I will introduce certain salient features of linear vector spaces and also point out to you towards the end of the lecture how exactly these concepts, mathematical concepts, become important in the discussion of physical systems. So today I'll talk about linear vector spaces. It's an introduction. Let's start with something we already know, which we are familiar with, and that is the two-dimensional linear vector space, which I will call R2, 2 for 2 dimensions. And you will have basis vectors Ex and Ey. You could also call them unit vectors I and j. This would be my notation. So any vector in this space, and this is a two-dimensional space, could be the plane of this table, the top of the table, or the plane of the blackboard, and any vector v in this space is some a times Ex plus b times Ey. So a is the component of v along the direction, the x-axis basically, because Ex is the unit vector along the x-axis, and b is the component of v along the y-axis. Now Ex and Ey themselves are orthonormal vectors. So I have the following, and Ex dot Ey equals Ey dot Ex is 0, and this is the dot product, the scalar product of two vectors. I could give a different notation. I could say the following: represent Ex by the column 1 0 and Ey by the column 0 1. Now if I did that, how do I generate the number 1 from this? Well, certainly if I take the row vector 1 0 and multiply it with the column 1 0, I get 1. So that's the same as saying that Ex dot Ex is 1. Similarly, if I did this, that too gives me 1, and that's the same as saying that Ey dot Ey is 1. And of course, if I did this, if I multiplied the row 1 0 with the column 0 1, I get a 0, and that's like saying that Ex dot Ey is 0, and so on. So I can associate with the unit vector Ex in 2 dimensions the 2 component column 1 0, and with Ey the 2 component column 0 1, and I have reproduced these relations in this notation. But this subtle change of notations tells us something, that indeed there are 2 types of vectors that we need to consider. One is the column 1 0 and the other is the row 1 0. Certainly that is not obvious here, but here I am able to distinguish between 2 types of objects, the rows and the columns. All these vectors, which can be expanded as a times Ex plus b times Ey, a and b being real constants, real scalars, are states in the 2-dimensional linear vector space R2. So basically, what are the properties of a linear vector space? I've started with giving you an example of a linear vector space, the simplest that I can think of. So what are the properties of a linear vector space? I have to define what happens to states in this linear vector space when I do addition or when I multiply by a scalar. Now if I have two vectors v1 and v2 in this space, there is commutativity under addition. That's certainly true. Take any two vectors of this form and addition is commutative. So that's the first property. There is also associativity under addition. By this I mean a vector, the over bar or the over arrow. I just use that as a notation for a vector. This is certainly true. For all vectors in this space, take any two vectors and you could add them, any three vectors, and you could add them like this. First add v2 and v3 and then add the result to v1, or add v1 and v2 and then add it to v3. Get the same answer. Now for a and b being real scalars, a plus b times a vector v is a times the vector plus b times the vector. So that's the third property. And then of course, if I have two vectors v1 and v2 and I multiply the result of the two vectors, the addition of the two vectors with a, that's the same as a times v1 plus a times v2. I can define a null vector. I define it as 0 ex plus 0 ey in this example of R2, and any vector added with 0, the null vector, gives me the same vector. Then I also talk about what happens because of multiplication by the number 1, that leaves the vector unchanged, and multiplication by the number 0, that just gives me 0. This is not to be confused with this. That's a vector, and this is just the number 0. So these are the 7 properties I expect of a linear vector space. It's very easy for you to check out that R2, the two-dimensional Euclidean space, all vectors or states in R2 satisfy these 7 properties. So this is the simplest example of a linear vector space. I can think of more examples. For instance, a straightforward extension of R2 is R3, the three-dimensional space where I have vectors Ex, Ey and Ez. So there are 3 unit vectors and these are normalized to 1. And they are orthogonal to each other, and so on. Now in this case, if I want to give column representations, column vector representations to Ex, Ey and Ez, I could think of Ex being represented by 1 0 0, Ey by 0 1 0 and Ez by 0 0 1. It is easy to check out that the fact that the vectors are normalized to 1 and that they are mutually orthogonal follows from this. I can talk of Rn where I have extended 3 to n. So, in Rn once more I can define n such vectors, each one being n componented with 1 as one of the entries. So, it would be 1 0 0 0 1 0, and this whole thing has n components. What is it that I have done here? Take this for instance. If I have a vector v which is 1 times Ex plus 0 times Ey plus 0 times Ez, that is really this vector 1 0 0. So, if I have a string of numbers, real numbers x1, x2, x3 to xn, this n tuple of numbers would represent a vector in Rn where the xi's are all real. I can now extend the concept further. Instead of having x1, x2 to xn, I can talk of the entries being complex. How would I define addition here, for instance? If I have the column x1, x2 to xn and y1, y2 to yn, how do I add these vectors? When I add them, the resultant would be x1 plus y1, x2 plus y2. So, there is a component wise addition, and if I have to multiply this string of numbers, which I can put down in this fashion, by a I mean ax1, ax2 to axn, where a is a real scalar. So, what I am trying to establish is that a vector in R2 or R3 or Rn is in general given by a string of numbers, real entries all of them, and the number of components here, you will have an n tuple of numbers if you are talking of Rn. The whole concept can be extended to Cn. This is the complex version of Rn. So, the entries would be Z1, Z2 to Zn, where the Z's are all complex. Once more we can check that Cn is an example of a linear vector space. Are these the only examples? That is not true. I can think of other examples of a linear vector space. In fact, I can think of function spaces. So, I want to define functions of x. Now, this is simply v1 of x plus v2 of x, where x is a real variable. And then of course, if a is a scalar and I wish to find this, that is the same as a times the function v1 of x. Now, given this, I can talk of linear vector spaces, examples of linear vector spaces being function spaces as examples of linear vector spaces, where I can talk of the manner in which functions combine to produce new functions. So, states in a linear vector space could be columns, could be functions, could be vectors symbolically denoted like this. They will all be states in an appropriate linear vector space, provided these properties are all satisfied by the states. There are some interesting linear vector spaces. Suppose you consider the string of numbers x1 to xn, the xi's being real, and suppose summation I equals 1 to n mod xi squared is finite. With addition and scalar multiplication defined as I mentioned earlier for an n-tuple x1 to xn, this space is a linear vector space denoted by L2, little l2, the space of square summable sequences. As I mentioned earlier, these would be like components along various directions, if you wish, Ex, Ey, Ez, and so on. And this property becomes important when we do the probabilistic interpretation of quantum mechanics, which is a very salient aspect, a very crucial aspect of quantum physics. The fact that summation I equals 1 to n mod xi squared, where these are the various components along the various directions in the linear vector space, if you wish, crudely speaking, then the fact that this is finite is an important input into the probabilistic interpretation of quantum physics itself. Similarly, when it comes to function spaces, suppose these are functions of x that I am considering. Suppose psi of x is a function of x, and in general psi of x is complex, then mod psi of x the whole square dx over the range in which x is defined. This could be minus infinity to infinity or any a to b. This less than infinity, where psi of x is a function of x, a space where this is defined, a function space where this holds, is called L2, the space of square integrable functions. And these two become very important in quantum mechanics. In fact, Schrodinger version, wave mechanics, the Schrodinger version of quantum mechanics uses psi of x, the wave function, which represents the physical state of a system. By mod psi of x the whole squared, I mean psi star of x, psi of x, where psi is in general a complex function and psi star of x is the complex conjugate of psi of x. I have therefore given you several examples of linear vector spaces ranging from the familiar column and row vectors, column vectors 1 0 0 1 and so on, to function spaces. So the first thing one understands is this, that a state in a linear vector space need not be a column, it need not be a set of real entries, n-tuples of real entries. It could be one of a variety of things. That particular linear vector space that we consider could even be a function space. In particular, could be the space of square integrable functions, or it could be a space of square summable sequences. So there are very many examples of linear vector spaces. The point is, one should be able to define addition and multiplication by scalars in such a fashion that these properties are satisfied, be they vectors of the kind that we know of in R2, or some columns or functions. We should be able to define addition of functions and so on. Now, one thing is obvious. Let us go back to this example. I see rows and I see columns. It is clear that rows and columns cannot be in the same linear vector space, because look at property 1. I cannot add a row to a column. Therefore, there is a linear vector space in this example. For instance, the linear vector space is one where there are columns. Different columns with entries are states in a linear vector space. Then there is a dual space. The rows, the corresponding rows, are members of the dual vector space. So, this brings us to the definition of dual spaces, the dual of a linear vector space. So, in our example, for instance, the columns 1 0 0 1 etc. are states in a linear vector space, are examples of states. This linear vector space does not have the rows and so on. As members of the linear vector space. The dual space corresponding to the LV is considered has the rows 1 0 0 1 etc. in it. Now, this aspect would not have come out if we had just stuck to Ex, Ey and Ez. And in that sense, writing Ex and Ey in terms of columns and also introducing the row 1 0 0 1 and so on in order to put down these relations in the language of columns and rows has helped us understand that for the linear vector space there is a dual space. This is merely an example. Every linear vector space has a dual space corresponding to it, and the members are in general different. Since we have a wide variety of linear vector spaces and I wish to study the properties of linear vector spaces in general, this is an appropriate time to introduce a very powerful and compact notation to represent the states of a linear vector space. This notation, given to us by Dirac, one of the founding fathers of quantum physics, one of the founding fathers of physics and quantum physics, the Dirac notation is as follows. All vectors in an LVS are represented by kets. What are kets? So, this is a ket, as ket psi, ket phi and so on. The psi is a vector, phi is another vector in the linear vector space. You can call it a vector, you can call it a state in a linear vector space. So, I put it like this is a ket. In the dual space, we have the corresponding bra vectors. I call them the bras. So, this is how you represent a bra. So, for instance, let us look at R2. 1 0 is a ket denoted by a ket, but I have to put down something to denote 1 0. Let me just call that ket 0. Then I have 0 1. 0 1 denoted by another ket. Let me call that ket 1. So, in the Dirac notation, the state 1 0 is denoted by ket 0 and the state 0 1 is denoted by ket 1. What about the corresponding notation for the rows? The rows 1 0 would be denoted by a bra, and since I have used the entry here to be 0 to denote 1 0, so that is the bra. And then 0 1, it is a bra with entry 1 because the column 0 1 had an entry 1 inside the ket. Then how do I represent the fact that 1 0 with 1 0 is 1? Well, this object is bra 0, this object is ket 0, and this inner product, I call it an inner product, is 1. Similarly, 0 1 with 0 1 is 1. In the Dirac notation is identical to bra 1, ket 1 is 1. And then of course, I need to worry about the fact that 1 0 and 0 1 are orthogonal to each other. I denote it in the following fashion. So, 0 1 with 1 0 is 0, that is identical, that is a bra, and since 0 1 is represented by bra 1 and this by ket 0, that is 0. Similarly, 1 0 with 0 1 is 0 is identical to ket 0 bra 1 is 0. This inner product is clearly the generalization of the dot product, because remember that this is the same as Ex Ey dot Ex is 0, and this is the same as Ex dot Ey is 0, and so on. So, in the Dirac notation, quite independent of whether the states concerned are columns or functions, quite independent of all that, I use this notation that all the states in the linear vector space are denoted by kets, ket vectors as they are called, and the elements of the dual space are denoted by the bra vectors. And this is a straightforward, powerful, universal notation that I can use for all scalar products or inner products that I form, independent of the kind of linear vector space that I am concerned with. Certain properties of the scalar product emerge. I can generalize this. So, if I have a state psi in a linear vector space, the inner product of psi with itself would be this object. And if psi were normalized to 1, look at this example for instance, 1 0 with 1 0 is 1. That means that this is normalized to 1. Remember, this is the same in the other notation to Ex dot Ex is 1. So, if it is normalized to 1, then the fact that it is normalized to 1 is represented in this fashion. In general, I can have the inner product of two different objects like this or like that. But it is clear that this thing is psi phi star. In the example considered, all the entries were real. However, in general, you know that the entries could be n tuples of complex numbers if you are talking about Cn. Then in that case, how do you go from the column to the row? Well, you will have to take a transpose. Instead of the column, you take a row, and every entry, its complex conjugate has to be put in. And therefore, if the element of the linear vector space has complex entries, then when you do the corresponding bra, every entry you have to take its complex conjugate, and therefore the general statement is that an inner product could be complex, could be a complex number. And it is clear that if you work with ket psi bra phi, this number is going to be the complex conjugate of that number. So, this is a property of the inner product. Till now, what we have seen is basically to make numbers, to make scalars out of the kets and the bras. The scalar that I got is the inner product structure. But many other things can be done. Apart from producing scalars, I can produce matrices. After all, this is true. Consider the same example that we had, 1 0 and 0 1. I can always construct a matrix out of this, given column vectors and given row vectors. But before we construct those matrices, let us look at some more properties of these vectors. I am looking at R2, but that is only a matter of convenience. It is an illustrative example using something that you already are familiar with. These vectors are linearly independent, because if I construct a vector v which is A times Ex plus B Ey, and if v is 0, it implies that A and B are 0. So, Ex and Ey are linearly independent. In general, I will say that a set of vectors are linearly independent in the linear vector space considered if I make a superposition of all those vectors. If that superposition is 0, then it follows, if it follows that the coefficients are all 0, then you say that the vectors which are used to form the superposition are linearly independent. So, Ex and Ey are linearly independent, and this can be generalized in a straightforward fashion to higher dimensions. So, that is linear independence of vectors. Now, this set of vectors, the set of linearly independent vectors, in terms of which all other vectors in the LVS considered can be expanded that means as a superposition, writing it as a superposition of all vectors, linearly independent vectors with coefficients a, b and so on. The set of linearly independent vectors in terms of which all other vectors in the LVS can be expanded form a basis set. In the same sense that Ex and Ey are basis vectors in R2, Ex, Ey and Ez are basis vectors in R3 and so on. Of course, to begin with, these vectors need not be orthonormal, they need not be normalized to unity and they need not be orthogonal to each other, but there is a prescription called the Gram-Schmidt procedure to make orthonormal vectors out of a set of basis vectors, and that can be used to produce a set of orthonormal basis vectors. So, there is a Gram-Schmidt procedure for obtaining orthonormal basis vectors. So, when I say basis states, I mean a set of orthonormal states which are linearly independent. I mean that the Gram-Schmidt procedure has already been used if initially the set considered was not an orthonormal set. And having used the Gram-Schmidt procedure, we obtain a set of orthonormal linearly independent vectors which form the set, the basis set. So, when I say basis set, I assume that orthonormalization has already been done. But one thing is clear, you need not have a unique basis set in any linear vector space. For instance, in R2, I can expand things in terms of Ex and Ey, or in terms of Ex plus Ey by root 2 and Ex minus Ey by root 2. The root 2 has been put in order to make this object, I can call this some vector little v1 and this little vx and this as little vy. You can check that Vx is normalized to 1 and Vy is normalized to 1, that they are orthogonal to each other. It follows from the fact that Ex is normalized to 1, so is Ey, and Ex dot Ey is 0. So, I can have several basis sets and I should be able to go from one basis set to another basis set. So, let us see how exactly this could happen. This could happen in the following fashion. Suppose I have a situation which is two dimensional. I illustrate it for a two dimensional situation and I have basis states psi and phi. When I say basis states, I mean this. Let me use the Dirac notation so that we get used to it. Normally, psi phi inner product would be phi psi complex conjugate, but that is 0. So, I can write it in this fashion. So, I have already assumed that it is an orthonormal basis set. Now, let me imagine that I have another basis set psi prime and phi prime in that linear vector space. This could be an example, psi and phi, psi prime and phi prime. In terms of column vectors, it is clear that I would have gone from psi to psi prime through a matrix, because if I had a column 1 0 and I need to go to another column, of course with the same number of entries, I would have done it with a 2 by 2 matrix. So, let me call that matrix U. So, in general I have psi prime is some u psi. Correspondingly, phi prime is u phi. So, what is the bra? Means interchange the rows and columns. That means, since this was a column, it would become a row. That means, take the transpose and take the complex conjugate of every entry, which amounts to saying take the Hermitian conjugate of this matrix and make that ket into a bra. So, psi prime bra is this. It automatically assumes that the column has become a row in the example that we considered, and every entry its complex conjugate is put in, and the Hermitian conjugate of u is taken. This Hermitian conjugate means take the transpose, interchange the rows and the columns, and take the complex conjugate of every entry. So, that is u dagger. So, what is psi prime? Psi prime. This is the same as psi u dagger u psi, but psi prime is again 1. I went from one orthonormal basis set to another orthonormal basis set. It is clear therefore that u dagger u is 1, because I know that psi is 1. Similarly, you can show that u dagger is 1. That means u is a unitary matrix. This is just an example. I will establish later that when you change basis and go from one basis set to another basis set in a linear vector space, you would be really using unitary matrices or unitary operators, as we call them, to move from one basis set to the other basis set. These are not the only matrices that we have. In fact, we have several matrices that we can form using the elements of the linear vector space. After all, as I remarked earlier, given column vectors and row vectors, we should be able to form elements of the linear vector space. You should be able to form matrices in the linear vector space. So, while this represents a number, what about this? This object is a column. Example, this object is a row. And that is the matrix. So, this is a matrix or an operator that operates on states. The operator operates on states. We will formalize and extend these definitions and explain them better in subsequent lectures. But right now, even in R2, let us look at the number of matrices that we can form. Let me call this M1, or let me write it here. Similarly, I can have 0 1 with 0 1, and I am going to call that M2. So, what is M1? This is M1, that is my notation. This is M2. Then I can have this. This is M3. I am just working with the basis states, nothing more. But it is clear that I can form several combinations and make many matrices out of these. And that is M4. Notation, the Dirac notation. This is 1 0 in my notation was ket 0, and 0 1 was ket 1. So, this is ket 0 and that is ket 0. So, this is the operator or the matrix M1, I am using the word matrix and operators interchangeably because I can represent operators by matrices. And this is a 0 1 and that is another 0 1. This is a 1 0 with a 0 1 and this is a 0 1 with a 1 0. Given these matrices, I can form a very interesting set of matrices, very interesting and very important set of matrices, which I will call the Pauli matrices. They are called the Pauli matrices. Sigma x, sometimes also called X, particularly in the language of quantum information and computation, and sigma x is 0 1 1 0. How do I get it from these? It's M3 plus M4. Then sigma y, also called y, that is 0 minus I 0, where I squared is minus 1. So this is minus I M3 plus I M4. Then sigma z, which I will call z, it is 1 0 0 minus 1, and this object is M1 minus M2, and of course the identity matrix, which is 1 along the principal diagonal, and that is M1 plus M2. The sigma matrices are very interesting matrices. They are Hermitian matrices because any of these matrices, if you take sigma x dagger, that means interchange the rows and the columns and also make complex conjugates of every element. So for instance, if you interchange the rows and columns here, it would become 0 I minus I 0, but take the complex conjugate and that will give you the same thing. Similarly, sigma y dagger is sigma y and sigma z dagger is sigma z. So I will call that sigma I dagger is sigma I. I can take values x, y and z. I denotes x or y or z. Then it is also true that the square of each of these sigma matrices is unity. You can easily check that sigma x squared equals sigma y squared equals sigma z squared is the identity matrix. Also traceless, that means the sum of the principal diagonal entries in the principal diagonal is 0. So these matrices are very important, keep occurring over and over again, particularly in the context of the angular momentum algebra. Quite apart from that, even at the level of quantum computation, which is a subject which is pursued very seriously in the recent past and at present, what is the effect of sigma x on 1 0? Sigma x on 1 0 is 0 1 1 0 on 1 0. And that is the same as 0 1. So sigma x on the state ket 0 is ket 1. You can easily check that sigma x on the state ket 1 is ket 0. So instead of the classical bits 0 and 1 with which you perform classical operations, you could think of quantum bits or qubits. I need to have physical realizations, I need to give examples of how to prepare these qubits. But suppose I did that at a later date, you could think of ket 0 and ket 1 as a quantum bit instead of 0 and 1, and then what happens is that the qubit 0 goes to qubit 1 and the qubit 1 goes to qubit 0. This is essentially the NOT gate operation that you know from a classical context. In that sense, sigma x becomes very important in quantum computing. It is a different matter that we have to find ways and means of actually carrying out this operation in a physical system. Similarly, if you look at sigma y or sigma z, what does sigma z do? Sigma z on 1 0 is 1 0 0 minus 1 on 1 0, and that just leaves it alone. But sigma z on 0 1 gives me minus of 0 1. In other words, it flips ket 1 and does not do anything to ket 0. So that is another important quantum logic gate operation which is carried out by the Pauli matrix. To complete the picture, there are of course many important logic gate operations, but right now to complete the picture I will talk about the Hadamard operation, and that just has 1 by root 2 1 1 1 minus 1. What would this do to 1 0? It just takes it to another state which is 1 1. I have the Hadamard operation. The matrix itself is this, and what does it do? You can easily check that when it acts on 1 0, this is E x, it takes it to E x plus E y by root 2, because this action is just 1 by root 2 1 1. Similarly, when it acts on 0 1, it takes it to E x minus E y by root 2. So, it changes the basis. You can also check that this is unitary, this object is a unitary matrix. I can also produce unitary matrices by exponentiating the Pauli matrices. Remember, the Pauli matrices are Hermitian matrices. So, H is a Hermitian matrix, and if I take the Hermitian conjugate of this, that is simply e to the minus I h. And therefore, if this object is u, this is u dagger, and it is clear that u dagger is the identity operator. Unitary matrices therefore find a very natural role in quantum mechanics, and all these matrices, Hermitian, unitary and other types of matrices, act on states in the linear vector space. How many states are there? In principle, an infinite number of states. Why? In the following sense, that even if you look at the example that I had, R2, where I had ket 0 and ket 1 as the basis states, I can form in general some state psi, I will call it ket psi, as A times ket 0 plus B times ket 1, and this is a superposition of the basis states. Suppose psi were normalized to 1, and given that these states are also normalized to 1, it is clear that modulus of A squared plus modulus of B squared is 1, and since A and B could in general be anything, I can form several superpositions. So, several qubits are possible given the basis states ket 0 and ket 1. There is a nice geometrical way of showing the qubits, and this is in terms of the Poincare sphere. So, I have this sphere of unit radius and this is the equatorial plane. So, that is the origin of coordinates. This is ket 0 and this is ket 1. Sphere of unit radius, and therefore, I know that the kets are normalized to 1. Any point here is represented by the coordinates theta and phi, where this is theta and that is phi. So, polar and azimuthal angles, that is the origin. So, I can represent any qubit here as cos theta by 2 ket 0 plus e to the I phi sin theta by 2 ket 1. And as theta and phi take different values, I get various qubits all sitting on top of the sphere. You can easily check when theta is 0, I get ket 0. You can also check that ket 1 follows from this definition of ket psi. So, this is a very nice geometrical way of picturizing qubits by using the unit sphere. If information is stored in a state, it means in principle an infinite amount of information can be stored if I combine several qubits or several superpositions. All of quantum computation and information, at least a large part of it, is about how to harness all the information contained in a qubit. Of course, once a measurement is made, ket psi would collapse either to ket 0 or ket 1, and that is about the information that you will get. Now, the other thing that I want to talk about, the other physical situation, the first one that I spoke about was in harnessing information by storing it in qubits. The other situation is in the context of angular momentum. I can use the Pauli matrices to define 3 matrices which I call the spin matrices Sx, Sy and Sz. These are of course 2 by 2 Hermitian matrices, and they satisfy what is called the angular momentum algebra. If I find the commutator of Sx and Sy, the commutator is this. By definition, the commutator of A with B is AB minus BA. Remember, these are matrices. So, Sx Sy is in general not equal to Sy Sx. If I find this commutator, I can show that it is IH cross Sz, where H cross is h by 2 pi, the Planck's constant. That is the Planck's constant. Similarly, the commutator of Sy with Sz is IH cross Sx, and the commutator of Sz with Sx is IH cross Sy. We will come across this algebra in the context of orbital angular momentum as well a little later, much later in fact, when we discuss orbital angular momentum. But right now, the point that I am trying to make is this: this angular momentum algebra Sx Sy is IH cross Sz, it is a cyclic thing. Replace xy by yz, yz by zx, is given in terms of 3 Hermitian matrices Sx, Sy, Sz. Instead, I can define an S plus, which is Sx plus I Sy, and an S minus, which is Sx minus I Sy. It is clear that S plus and S minus are not Hermitian matrices, but S plus dagger is S minus and S minus dagger, this is plus and that is dagger, is S plus. Dagger means Hermitian conjugate. Interchange the rows and columns and make complex conjugates of all the entries. The algebra translates, and you can check this out, to this. If you find the commutator of S plus with S minus, this will be 2 H cross Sz, and if you find the commutator of Sz with S plus, it is plus H cross S plus. Instead, if you found the commutator of Sz with S minus, it is minus H cross S minus. So, commutator of Sz with S plus, you can check using this as an input that the commutator of Sz with S plus is plus H cross S plus, and the commutator of Sz with S minus is minus H cross S minus. So, this algebra of the spin matrices can be either written this way in terms of 3 Hermitian matrices, or in this fashion where S plus and S minus are not Hermitian matrices, but are Hermitian conjugates of each other, and Sz, which is a Hermitian matrix. Where does this fit in which physical context? I will discuss the problem of the 2-level atom in my next lecture, where I will extensively use these matrices and their algebra. As you know, in quantum mechanics, energy is quantized for most physical systems. So, not all energy values are allowed, but energy values say E1, E2, E3, E4 and so on are the allowed energy values for a given quantum system. In the case of the hydrogen atom, these values are unequally spaced, and as you go to higher and higher energy levels, they are so close they look like they are almost continuous. In the case of the linear harmonic oscillator, these energy levels are equally spaced. A 2-level atom is one where 2 of the energy levels are so close to each other that by pumping energy, I can take the atom from one energy state, from the lowest energy state to the next state, but the other states are so far away that it is difficult for the atom to go to that state. So, it is really this 2-level atom where this would be called ket 0 and that would be called ket 1. I will have these 2 states. The linear vector space is a 2-dimensional vector space, and I will talk about the matrices or operators which will take you from this level to that level and vice versa and so on. That is where these spin matrices become very important. So, I will discuss the 2-level atom tomorrow to give you a specific physical situation where the algebra of the spin matrices become important.